Okay, thank you for attending. My name is Doug Bell, and I work with Colomar and Ring Technologies. We're going to be presenting what's ahead in Thermal Desktop Suite and also provide a few feature demonstrations as time permits. Uh, just to start, if you have any uh, questions, you can type them into the streaming chat, and we will get to them as we can. Uh, if you are having trouble um, with refresh or the stream, it's good to refresh. I think I've heard that Firefox has troubles and may not show the chat, so try Chrome or another browser. Uh, and I think a lot of this information is going to go into the chat in the stream itself. So with that, I'll go ahead and get started. So in this presentation, I'm going to give an overview of CRTech products. Um, I'll go over some new and upcoming features covering Thermal Desktop User Interface that includes RadCAD, FlowCAD, Thermal Desktop, also TD Direct, SendaFluent, and then I'm going to pass over to Matt Garrett to discuss OpenTD. And as time permits, we'll do feature demonstration, but we may be asking questions first and then jumping into that to see how time works out. So a little bit of background about myself. I have a degree in aerospace engineering from North Carolina State University. I've been with CRTech since about 2006. Got started with thermal analysis back in '93 using traces and Senda, and that would also be the first year I attended TFAWS. Prior to joining CRTech, I worked for NASA and Lockheed Martin. So over all that time, I've worked on stratospheric airships and balloons, re-entry vehicles such as X-33, missile launchers, and on-orbit spacecraft. So CNR Technologies has a tool suite that starts with Thermal Desktop as the modeling environment. So this is the graphical interface. It is based in AutoCAD. And you can also license modules for RadCAD, which performs thermal radiation, orbital environments, and FlowCAD is another module for modeling heat pipes and fluid networks. The engine itself, the solution engine, is SendaFluent, and it runs in the background. So you pretty much have one interface for your solution. Now, TD Direct is something that we have put into ANSYS Space Claim, and this is more of an upstream tool where you can create or import CAD geometry, mark it up, set up some advanced meshing settings, and then import that meshed model into Thermal Desktop. So looking at it from a more graphical view, so we've got Thermal Desktop, which is our graphical interface, and it communicates sending the network and user logic into SendaFluent for the solution, and then the results come back into Thermal Desktop for post-processing and plotting. RadCAD fits into Thermal Desktop for the radiation simulations and environmental heat loads. Also, I mentioned FlowCAD for fluid network generation, piping systems, complex tanks. And Thermal Desktop on its own within the AutoCAD framework can read in CAD geometry where it would be used as construction geometry. There are some basic meshing tools, but we'll get to more complex meshing shortly. The mesh can be either sent to a structural model or you can read in from a structural model, but more often people are mapping temperatures onto structural models, which is beneficial in that you can model the thermal model for what's important for thermal, typically volumes and areas, and the structural model can focus on what's important for structural features like rounds, fillets, holes, things like that that can cause issues with stress. Now, TD Direct is yet this other tool that fits in, and this is for your advanced mesh generation. So you can mesh within Nastran or FEMAP or ANSYS and bring that in, or with TD Direct, we actually have two-way communication with space claim. So if the geometry changes or you want to change your resolution, or even send parameter values back up into space claim to change the geometry, the mesh comes right back in. Everything is reconnected automatically. So you get a nice one step, one click update. Then there's various analysis integrations. You can connect to Excel, MATLAB, CFD. Most of those are all improved with OpenTD API, which I mentioned Matt will speak to a little bit. So we've been working on that and improving it so that you can have these communications or even do programmatic model building and modification. So thermal desktop is where it will generate the thermal network based on the geometry. You discretize the geometry either with finite elements. They could be internally meshed or imported from another tool, or finite difference surfaces and solids. These use finite difference conduction assumptions, so they solve fairly quickly. But what's really nice about and powerful about these is they're mathematically correct surfaces. So their shapes are resolution independent. A cylinder is a cylinder, whether it's one node or 1,000 nodes. Parametric modeling, so you can parameterize these things. So looking for goal seeking or optimization of dimensions and sizes and shapes, things like that. And then lump parameter is non-geometric. So let's say the air in a room, you can represent it as a lumped parameter temperature. And of course, Syndifluent is a little more under the hood. It's a single user interface for model creation, radiation calculations, solution initiation, and then post-processing, all of that in Thermal Desktop. There is also what's called a dynamic mode, which allows the solution to drive information back in the graphical interface. So if based on the temperature you want to change the size of something, you can do that, or reposition a radiator or anything like that. So a little more on finite difference surfaces and solids. Like I said, they're mathematical surfaces, so their shapes are independent of the resolution. So you add resolution to capture temperature gradients, not to capture the shape. And they're very accurate for radiation reflections. They're parametric, and you can snap them to geometry so that you can match up the dimensions. And so here an example would be a parabolic trough, as in this solar collecting system. The focus of the analysis is on the tube running down the middle, but the shape of the trough is very important. So here it's modeled with a single node, so it doesn't take up calculation time. We're assuming it's all one temperature, but then the reflections are all exact into the center line of that pipe, so we can then focus on that portion of the analysis. But if you do need to look at temperature gradients to then pass on to structural analysis for warping or anything like that, you can certainly do that. Looking at RADCAD, we'll calculate surface to surface and environment to surface radiation using either Monte Carlo or radiosity methods. You can do gray body assumptions or do non-gray radiation through wavelength bands. There's also environmental source trackers that you can add in. So looking at the image on the right, you could be sun facing while you're in the sun and then earth facing while you're out of the sun. So all of that can be added in and automated. So with FlowCAD generates the fluid network, and it can be either based on geometry or sketchpad. Um, and you can combine the two, as you'll see in a few pictures here. Uh, the pipes and heat pipe objects are available, so you can easily build up piping networks along with not just the fluid, but the pipe wall and the heat transfer between the pipe wall and the fluid. And those can be involved in radiation. And then we also have a method for modeling heat pipes and estimating their behavior. Um, we have complex tanks or vessels, and then all of this can connect to the thermal surfaces and solids so that you have heat transfer between the fluid and the structure. So just a few examples that show, um, even combining geometry and non-geometric, um, tank filling. Here's another parabolic trough where, this may be meters and this could be, kilometers until you get to where your thermal storage is. So you don't want to draw all that out to scale. So you've got non-geometric portions to your network. And then another example of an LNG tanker. So ANSYS Space Claim we found is a very powerful tool for what's called direct modeling. So it recognizes the topology of the system. So it's push-pull CAD geometry creation and modification. I found it very easy to learn and use and retain that knowledge. And you can import just about any CAD format file and bring it in and work on it as though it had been built right there. And you can clean up, heal, defeature, even with what's called dumb geometry, such as step and IGES, which has no understanding of features or anything like that. And then you can prepare for analysis. So you can mid-surface um, geometry, you can extract volumes, pull off center lines, project contact areas, and then tag up thermal features such as materials or submodels or heating zones or boundary conditions. And you can control the meshing as well. So TD Direct, that feeds right into TD Direct, which exists in both Thermal Desktop and Space Claim and communicates back and forth between the two. Where you have advanced meshing with quad elements, you could do non-manifold meshes, you have localized control, merging and matching the meshes between different parts, and even curved elements, which gives you this nice shape here without high resolution. Set up property assignments, both radiation and thermophysical, and mark things up for boundary conditions, as I said. And then your updates are one-step updates. If you modify the geometry, you synchronize between Thermal Desktop and TD Direct, and it brings in the new mesh, and it's reconnected exactly as you defined it. So some of the strengths of Cullimore Ring Technologies, we're very strong in thermohydraulics, especially two-phase. We have many unique applications that can't be solved any other way. And we're very strong in the thermal radiation and orbital environments. We do have unique tools for aircraft fuel tanks and space and launch propulsion systems. If you look at the examples I showed with FlowCAD, tanks that can be partially filled or draining, so we get the heat transfer correct from the wetted surface and the dry surface. We also have some very unique strengths in user extensibility and customization, and that's still improving, as you'll see shortly. So we're competitive as is for new technology or new design questions for old technologies. So a lot of R&D users love our tool. And we also have a unique focus on system level or vehicle level transient thermal design simulations. So putting together the native geometry which can be very low resolution, the curved elements, which allows you to capture the shapes and volumes without high resolution, compartments, this automated calibration to test data. All of these things help you build up a fast running model that works better, especially once you start calibrating to test data. That's always going to give you the best model. So, Matt, were there any questions that came up during that portion?
No questions so far, Doug.
Okay, great. So we have some recently added and upcoming features. So you'll notice a few of these, I'll indicate 6.2, which is an upcoming feature. So that'll be in our next release, which is currently scheduled for the fourth quarter of this year. If you see 6.1, it's been added to the current release. If you don't see it in your version, make sure you get to the latest patch so you can get that feature. So with thermal bodies, whether they're finite difference or finite element, we have enhanced the insulation capabilities so that thin shells and finite difference solids can use either offset ID, submodel for a single layer, or submodel with offset ID for insulation nodes. So prior to this, I think FD solids could only do the offset ID. But then this submodel with offset ID and or insulation nodes is new to both thin shells and finite difference solids. For finite difference shells and solids, you can now have the internal axes drawn in wireframe mode. So this helps you understand the face and edge definitions of your system. So when you're making up contactors or heat loads, anything like that, you need to know which is the minimum X and maximum X. So red is X, green is Y, and blue is Z, so that you know which is the correct edge, which is the one you need to apply the contactor to. For heat loads, heaters, and conductors, we've now extended to allow applying them to the edges of thin shells. So that you can work with models that use thin shells so that you're just getting the lateral conduction, but you can now apply contactors just to the edge or heat loads just to the edge. And then heaters can now be applied just to a single node instead of requiring a surface or a solid for those. Now, this is a pretty big change here with pipes. Pipe center lines can be placed into domain tag sets. And those domains can be assigned to curves within TD Direct and then exported to Thermal Desktop. So, and then the pipes can reference a curve domain tag set for their center lines. So the bottom line of this is now pipe center lines can be modified in TD Direct with updates changing the pipe that references that domain tag set once you synchronize between the two.
Hey, Doug, there's a question.
Yes.
Sure. Hume's asking, for elements, will it show edge 1, 2, 3, 4?
I would have to check on that. I'm not sure if it does or not. We do have, and I recently, or no, I don't think I've posted the video yet, but I recently worked on a video that actually shows ways for edge contactors to make sure that you get the right edges. And there are ways to, if you right click in the field for the from objects, for finite elements, you can ask to pick only the free edges of the group of elements that you picked. So then it excludes anything that's an internal edge and only picks the edges that are exposed.
And he's clarifying in relation to solid axis display.
Yeah, I'm not quite sure if that's going to work or not. I would have to check into that. Now with, were there any other questions, Matt?
Nope.
Okay. With FlowCAD compartments, some of the things we've been working on, we now have a new register generation system. So this allows various compartment inputs to be inspected or changed during the send to Fluent execution. We've also got a new tie multiplier. Most ties use UAM as a multiplier on the tie heat transfer, but compartments already take control over those. So we've added a new parameter for that. And also splash and spin. I mean, it sounds like a washing machine, but this allows specification of a splash zone near the liquid surface. So you can look at fast small slosh or froth when boiling, things like that. And then provisions and examples for use in axial spin, such as barbecue rolls at low gravity. With thermophysical properties, we've made some changes with phase change materials. They've been enhanced in the next release. They will automatically tally the melt fraction by submodel, and then we're now allowing phase change materials to mix with non-phase change materials in laminates and aggregates. So you might be modeling metal fins or a mesh matrix within a container of wax, and you want to include the different components of conductivity and
Question,
density.
Doug.
Yes.
What does the splash zone do thermally?
Well, you would see a cool spot on the wall where the um, where this splash has occurred. So you have a brief moment of um, wetting on the surface, and then an evaporation most likely. Uh, so that's going to cool off a portion of that wall.
And another question. Just wondering if the axial spin is manifested as like fluid as a rigid body parabolic surface calculator.
Yes, unfortunately, I'm not familiar with that example, so um, I can't answer to that one. But you can certainly write in to support@crtech.com, and you will have the appropriate person answer that for you. All right, so another thing we've added in with phase change materials is that at the container boundary, so you have a phase change material in a container, we allow you to merge the nodes between the two, and it will continue calculating so that you can use the properties of both materials. And this avoids adding a large contactor value, which can usually overtake your solution time step. We've added in property options for accretion, where accretion is the buildup of a substance such as ice on surfaces that will affect the heat transfer. Uh, we've had the recession feature, so this is simply recession in reverse, where recession is you have a material that when that heat is added, it loses mass and reduces in size. So this is just the opposite. You're actually building up on the surface. Then for aggregate materials, we've enhanced them to perform a model check or a volume fraction check. We realized that we were allowing volume fractions that did not sum to 1, and that plays havoc with the calculations internally. So we are providing a check for that. We've also in 6.2, we'll be adding in a mass fraction option as well, and the option to override the calculated properties. So you might have an aggregate material where you know the conductivity from a vendor sheet, but you need to calculate the density and specific heat for the bulk. So you can certainly do that and then override the conductivity with the known values. In case sets, we have an option to allow exceptions for duplicate node checks. This is pretty powerful because many people use duplicate nodes for modeling techniques, and you always get a message that says, yeah, this is a duplicate node. Well, now we have exceptions so that you can use those duplicate nodes without interfering with the test, and the test can then check for other duplicates that were not intended. The model kicker, which is a great tool for checking your model by running a series of steady state solutions where some portion of the model has been kicked, say by 1 degree, and then it compares the difference in temperatures between the results. And where you see, those differences will show the strength of connectivity in the model. We're now allowing boundary nodes to be kicked within 6.2. And then along with the accretion properties being added, we've got now accretion settings added into the Synda control. For post-processing, color bars can show area or volume as a percent. So we have an option for that now. And this is very useful for element quality display. So where we show the skew of elements, it's good to know what fraction is at what level. So you can certainly see that. Hopefully you're skewed more to the lower end of the scale with very few elements up at the higher towards a value of 1, which means a degenerate element.
Quick question.
Yes.
Hume's asking if the duplicate node checks are implemented by submodel or wildcard range, or if you have to list them explicitly.
I'll have to look into that. I think it was by the wildcard. So it's most likely a typical node list option, but I don't recall right offhand. We've added in lump species into thermal desktop post-processing. So when you're dealing with multi-species fluids, you can now post-process those through thermal desktop. Within version 6.1, we've added conductor G and HR, where G is the conductance and HR is the heat rate through the conductor. We've added those to the save results to text option. And then user-defined Fortran arrays, which are sized to nodes, lumps, or other network objects, can be referenced by the UDFA name dot submodel name dot ID. So instead of having to know the exact element ID or element within the array, you're now assuming that they are aligned perfectly with the node temperatures, lump temperatures, lump pressures, things like that. So this effectively allows you to create user-defined variables for network objects. So you might want to calculate the node on enthalpy or calculate the path velocity, things like that. So when you're in the save results to text or the TD text, which we also call smart annotations, you can reference them very easily within that. Within the logic manager, we've actually added in convergence waivers so that you can exclude objects from convergence checks. So if you have a system that is not converging well, but it's because of one part that you know will never converge, such as a specific heater or something like that, then you can exclude that from your convergence check. And then again, more expansions on the user-defined Fortran arrays. They bring an amazing amount of power to solutions. So we've already created several examples for recording a minimum, maximum, and weighted average temperature per submodel, creating user-defined variables such as path velocity, and creating unique heater control systems. So I had one person ask, I have 4 measurements, but the heater is controlled to the second highest temperature of those measurements. So using UDFAs, we were able to set up a way to do that. We're adding in logical arrays to use as masks and functions. So when doing minimum, maximum, or sums, things like that, you can actually mask off portions of arrays within Fortran. So then these logical arrays allow you to set those up and define those masks. And we're adding character arrays as well to the user-defined Fortran arrays. And then UDFAs can be individually controlled for output to results files. So just a checkbox that says include this in the results, or you can clear it to not include. So you might be using a logical array to do some calculations, but you don't want that taking up space in your results. So you can exclude it from your results. With network element logic, in 6.1, we've added the ability to right-click in the input field and get a list of the operators as well as the symbols that you have and some constants. So you can choose from those very easily. In 6.2, you're going to have access to the UDFAs as well. So when you're writing up your logic, you can pick that information and you don't have to remember exactly how to spell it out. Now with thermoelectrics, I always struggle with that one. Thermoelectric coolers and thermoelectric generators have been enhanced with registers for the Seebeck, the resistivity, and conductivity. That was included in 6.1. And then we've also added in leg level calculations. So this allows advanced thermoelectric designs to be simulated, including distinct p-doping and n-doping leg materials, aspect ratios, even number of legs. And it also enables segmented legs with user calculated composite leg properties. Now for radiation calculations, this came in the middle of 6.1 as we've started writing out RAD-Ks and heating rate arrays. You can choose whether they're going to be written as ASCII or binary files. Previously, they were always ASCII. Binary files decreases the pre-processing time and also file generation time, and probably even improves interpolations. With the boundary condition mapper, which allows you to apply external information such as heating from CFD onto your thermal model and map it, we're improving the mapping so it'll search for a single object and probably flag where you have equidistant objects so it doesn't know which one to pick. So that's an improved mapping. We've been using that one for the structural model mapping, data results mapping for quite a while now. And also conductor and temperature pairs have been enhanced so that you have binary arrays to improve pre-processing, send file generation, and also the interpolation. Now, a few things that have changed in TD Direct. Some of these we've added in 6.1, some are coming in 6.2. You now have an option to suppress for physics, to set and also view within TD Direct. Suppressed objects will not be meshed. That's a little bit different than a geometry only, which actually meshes, but all of the elements are turned off or disabled for the solution. Now that's a great way to, that not, or geometry only option is good for getting matched meshes across a gap. But this is actually saying this object should not be meshed at all. Domains with matched regions will generate a free domain of unmatched regions. So matched regions are typically locations of contact, and when you're making the contactors, you look for the matches. Unmatched regions would be anything that's exposed. So you might add in convection right beside where you have contact. So that's what this allows. Curves can be used to align material orienters. So we're adding that into 6.2. And then, as I mentioned before, curves and lines can be assigned to domains in TD Direct and then exported to Thermal Desktop for use in pipes.
Question, Doug?
Yes.
For the binary RADKs and heat rate files, will there be a way to read them and output contents as ASCII?
So there will be an ASCII file that's written out so that you can see what was generated and take a look at them. But then Cinda would then read the binaries and work with those specifically, so they can actually skip the whole pre-processing. All right, let's see, yes, I got through that. So Cinda Fluent, we have a path linker utility that helps split and join fluid submodels. This is often required to change working fluid descriptions within a flow system because you might hit temperature range changes or condensable mixture limits, things like that. You can also make one or more tanks act as temporary junctions and transients. So this avoids having to have multiple drawing files with different tank versus junction decisions. And then iFace velocity query for advanced valve modeling or simulating moving liquid slugs has been now added into that solution. I don't know if you caught our presentation yesterday, but co-solving with ANSYS Fluent, we've partnered up with ANSYS to integrate CRTech simulation products with ANSYS simulation. I'm not going to go into all the details of it, but in 6.2, you will have access to conjugate heat transfer with radiation and 1D fluid flows. Tim presented a few examples where you have, CFD results on the outside here, but FlowCAD is solving the fluid flow inside the tube. So it is easy to use, assuming you have a proficiency with Fluent and Thermal Desktop. And system coupling is well documented. System coupling is the ANSYS tool that allows this. And the advanced coupling algorithms have been added in for stability and speed. And then this will be a built-in feature. You obviously have to have the licenses of Fluent and Thermal Desktop, but no additional license would be required. All right, so I'm going to turn over the presentation to Matt, and he will talk about OpenTD as long as there are no questions at this point.
Okay, thanks, Doug. Let me just share my screen.
Let's see, I see there is a question here. Can we use this good stuff to determine global warming or cooling? Well, I certainly can't see why not. I don't know that anybody's done that. If a model is a model, so you have a certain amount of absorption, you have so much reflection, and things like that. So there would probably be some assumptions you would have to come up with to add it in. But I mean, I don't see why it couldn't be evaluated with this.
Okay, I'll take over. Thanks, Doug. Thanks, everybody, for joining our session. And thank you, Parker and Zeta and all of the other organizers for putting this together. I'm Matt Garrett. I'm one of the developers at CRTech. I've been with CRTech for about 7 years. Before that, I did thermal analysis for about 12 years on shuttle and 787, bunch of stuff. And I'll be talking about OpenTD, which is our new API for Thermal Desktop. Okay, so if you're not familiar with OpenTD, I'll just give a quick overview. As I said, it's an application programming interface, or API. What does that mean? Well, that means that you can write programs that talk to the API and then control Thermal Desktop without interaction. It's installed with Thermal Desktop 6.0 and above. It had a different name in 6.0, but it's the same thing. You can access it with any language that can talk to the .NET framework. We recommend using C#, but people have used it successfully with MATLAB, Python, PowerShell, a bunch of stuff. It's version controlled. And what does that mean? That means that when we release 6.2, if you've written a 6.1 program, or you've written a program that works with OpenTD 6.1, it won't break. If you want to upgrade and start using the new features that are in OpenTD 6.2, you can do that, but you don't have to. And it's documented. There's a getting started guide and a class reference document that are installed with Thermal Desktop. Plus, we have a bunch of additional examples on the forums. Okay, so what can you do with it? Well, you can connect to an already running instance of Thermal Desktop or start a new instance. And in fact, you can connect to as many instances of Thermal Desktop as you want. So you could have one client program that is talking to two instances of Thermal Desktop and trading data between them. What kinds of things can you do once you're connected? Well, you can create entities, you can query existing entities, edit them, delete them. What kind of entities? Well, all of the CINDA-fluent network entities like nodes, conductors, lumps, paths, etc. But also finite different surfaces and solids, also FEMs, case sets, orbits, material properties, optical properties, and a lot more stuff. When you're working with those things, you can seamlessly work with units, symbols, and expressions, just like you do in the GUI. So anywhere in the GUI that you could enter an expression referencing a symbol and set the units of that expression, you can do the same thing in OpenTD. You can run cases, and then once you've run those cases, you can explore the solution results, compare them to each other, and plot those results, all just using OpenTD. I'll show you a quick demo of OpenTD. This is just OpenTD 6.1. So all of the capability I'm showing here is available to you right now in Thermal Desktop. In this scenario, you've been given a model of some sort of electronics box. And it's got a, I wonder if I can run my mouse around. I don't know if this will come through on the stream very well, but I'll give it a try. It's in an
Matt,
aluminum, yeah.
Before you get too far into this, there's a question, can we interface through OpenTD with mapper objects?
Not yet, not planned currently for 6.2, but send us an email to support@crtech.com and we can discuss it.
All right, thank you.
Okay, so in this scenario, I've got this, this electronics enclosure. There's an aluminum box. There's a motherboard down here on the bottom, a bunch of daughter boards on this motherboard, and then a bunch of chips on the boards. And this model came to me with everything on one layer and everything in one submodel. And the heat loads I wanted on the chips hadn't been applied. And so I could painstakingly modify this model by hand, or I could use OpenTD to try to organize this model. And so I'm going to use OpenTD, of course. And so what we're able to do is using OpenTD, we can query the AutoCAD database and say, give me a list of all of the rectangles. So it does that. And then we can use this technology called LINK that is available in .NET to make these declarative statements about what we want to get out of that list of rectangles. So we can say, hey, get me all of the rectangles that have material aluminum and stuff those into a list of enclosure rectangles. And get me all of the rectangles that are this dimension, and that's going to be such and such a chip. Put that into a list of chips. And then apply a heat load to those chips, but make a symbol control that heat load. So we can do all that stuff. Another thing we did in this model is all these daughter boards, we said, well, find the position of those boards and then put them on different layers based on their Y position, in this direction, and change their color. So they're easy to look at. So I'm going to run this video. I don't know how well it'll come through in the stream. Everything happens pretty fast, but here it goes, organizing our model for us. Okay. Okay, let's talk about new features in 6.2. So we have support for more thermal desktop entities than we had in 6.1. We've added support for finite difference solids. We've got much better support now for FEMs. In 6.1, you could create a FEM, but you really couldn't modify it. You couldn't query the elements, etc. You can now do that in 6.2. There's support for compartments, and there's support for contour plots. So imagine this situation with contour plots. You can run your model, and now you can say through OpenTD, choose this data set, choose this time, and maybe you figured out what time you wanted to look at by querying the data set and finding some max temperature or something. You say, choose this time, draw me a contour plot, turn on and off these layers, restore this named view, so I'm looking at the view that I want, and take a screenshot and save it to this file. And then, maybe your program could pull that file into a Word document or something, or not. Anyway, that's what you can do now with contour plots in 6.2. We had support for case sets in the earlier versions, but now we've got support for running batch runs in the case set manager. Before you had to look at each case set by itself. Now you can set up batch runs and run them just like you're running in the GUI. We have support for pressure loads and a bunch of new AutoCAD entities, a bunch of line types. We have support for new logic objects, the PID controller and array interpolation. We're going to give you access to the QFlow manager, and then the new user-defined Fortran arrays that Doug was talking about. We'll give you support on the thermal desktop side in OpenTD to create them in your model, and then support on the dataset side to read them. This is a quick demo of using the new finite difference solids in OpenTD. It's kind of a silly example, but it'll be available on the forum later. I think it's probably the first game implemented in thermal desktop. Okay, I'll move on from there. So some other new stuff in 6.2. In 6.1, you can read save files and CSRs. So you can get all the results out of save files and CSRs. But if you wanted to find model topology, what conductors are connected to what nodes? What ties are connected to what lumps? You couldn't do that. I mean, you could. You could open the drawing file with with OpenTD and try to deduce that topology from there. But you couldn't directly do it from results. Well, you can now in 6.2. There's a file called the PCS file. You can now read that and query it to find model topology at each record. So if the topology is changing during the solution, you can see that now. And then we have another class that kind of layers on top of that called the results browser. And what this does is it takes that new PCS object and combines it with a data set and figures out heat maps between submodels or arbitrary groups of nodes and lumps. Okay, we're handling missing data from records in a more graceful manner than we did before. So a common example of this used to be that the default on a save file was that you would save register values at the beginning and the end, but not in the middle. And that wasn't really handled in earlier versions of OpenTD. But in 6.2, if you call a getData method on a data set and that data doesn't exist at a record, it'll return not a number. And then downstream in OpenTD, the plotter and the derived data arrays, and we'll talk about those more in a moment, now understand how to handle not a number in a clean way. So the example I'm showing here is I've tried to plot data from a save file where we only had register data at the beginning and the end for this orange series, and we had temperature data all the way through. And so the plotter receives those that array for the register with not a number for all of these records, and it says, okay, well, I just won't plot that stuff. And any series with a discontinuity like this, it says, okay, well, I'll automatically turn on markers. So you'll see your data. You can override all of that, but I tried to make it work in an intelligent way by default. And the same goes for derived data arrays. So what are derived data arrays? These are these objects in OpenTD that take a collection of input data arrays, and then when you try to do something with them, like plot them, they perform an operation on that set of input arrays. So there's one called an average data array, and at each record, it just finds the average value of the input arrays. And so this new not a number functionality, I tried to make it smart as well. So if in your derived data array, one of the input arrays has not a number at a record, then that just flows through into your results from the derived data array. It'll show not a number as well. You know, I don't want to hide the fact that you don't have data at that record for one of your input arrays. There's a Boolean in derived data arrays that can let it ignore that, but the default is that it'll just pass that information on to you. You can now read text transient files and general spreadsheet files. And you can treat them just like other data sets. So we have an iDataset interface that has a bunch of methods for get the node names that are in this thing, get the data for such and such a list of nodes, get the data for such and such a submodel. And that's how you talk to save files and CSRs in earlier versions of OpenTD. Well, now you can talk to text transient files or just to like a general CSV file as if it was a data set. So it should make it easy to add test data into your post-processing and compare it with model data. We've added a few new derived data array types. So we have a max data array and a min data array. And what they do is at each record, they return the extreme values. We had something similar in 6.1 and still do called select max and select min, but they don't find the extreme value at each record. So this is just a different way of finding max and min. We've added a weighted average data array. We already had an average data array, but now you can weight that average based on information that either you provide externally or that you pull out of the data set. And I'll show an example of that in a moment. And then we've added a formula data array that, again, takes a list of data arrays, but then the operation that it performs is an arbitrary formula that you enter, and that formula is units aware. And I'll explain what that means in the example. So here's a weighted average data array example. where we said, hey, get me all of the node temperatures for the plate submodel and plot all of them. So it did that. That's all the lightweight lines. And then we said, also create a weighted average data array and use the input temperatures, but weight it by thermal capacitance. And so that's what this heavy line is. So it's easy with this tool to find an MCP weighted average temperature. And this is an example of the formula data array. This is the one that takes the arbitrary formula and uses it to operate on the input arrays. So in this case, we've got two input temperatures, the two lightweight lines. And then the formula data array that we created is this thick red line. And what we asked for was, please find the quotient of these two input temperatures. And of course, it doesn't make sense, well, probably doesn't make sense to divide degrees Fahrenheit temperatures. And so when we defined the formula data array, we told it, hey, when you perform your operation, do it in Kelvin. So it doesn't matter how we're presenting the information. We tell it, hey, when you perform this operation, do it in Kelvin. And so it does. Okay, and then we've added some new ways to compare data sets. So in the older version of 6.1, we had an object called a comparer. And you can define a comparer that points to two data sets, so two save files, CSRs, text transient files, whatever, okay? It points to those two, and then you tell it what you want to compare. I want to compare all of the node temperatures. I want to compare all of the thermal submodels, okay? There's a big, huge list of configuration switches you can throw on a comparer to choose what it's going to compare. In 6.2, we've added something called a compare suite that will take a bunch of these comparers and assign a compare assertion to them. So I'm asserting that they'll be the same, or I'm asserting that they won't be the same. And then you can run the compare suite, and it runs all of those comparisons and tests your assertions. So it's sort of graphically presented here. Each row represents one compare assertion. So I'm taking some baseline data set, I'm comparing to a copy of it, and I'm asserting, yeah, that's the same. And I'm taking a baseline data set and I'm comparing to one that was using a different orbit, and I'm asserting that they shouldn't be the same, etc. When I run this suite, it returns results. It returns results of my assertions. So in this case, it said, well, 3 out of your 4 assertions were correct. And then this is just a small excerpt of the string that it returns, but it returns this giant string explaining how it doesn't work out. You know, this one, it's going to say something like the node names didn't match, or whatever, for submodel main, or whatever. Okay, in 6.2, we already had Tim Panzak presented an extensive presentation on this yesterday, but in 6.2, OpenTD will give you the ability to communicate with SynDefluent, which you can use for co-simulation. There's a bunch of miscellaneous new features. I'm not going to read all of these, but you'll have access to this presentation afterwards, and you can take a look and see if there's other good stuff here. And then there's some performance improvements as well for results reading, mainly. This has all been updated in 6.1 already. So if you get the latest patch, then you should find that save files, CSRs, the comparer class, average data arrays, and getting data for groups of things that returns a data array collection. So like all the node temperatures for a submodel, for example. You should find that those things run a lot faster than they did when 6.1 was released. And then the save file class is now thread safe. Okay, that's all I have. Doug, were there any questions?
Yeah, there's question here, how can TD Direct or OpenTD be used to convert models from Thermica, Maya, or other software packages? I'll start with this, and you might be able to expand on it. TD Direct wouldn't be the tool, but OpenTD has actually been used to create a converter for ESA. And if you go to their, I'm trying to remember the name of it, but if you go to their website,
It's the
they actually do
taskverter
have,
page.
say that again?
It's the taskverter page.
Taskverter, yes. If you go to the Taskverter page, they've actually used OpenTD to create a converter between ESA models and thermal desktop models. And that's pretty much the way we're looking at this is OpenTD could be tied into the API of another tool to communicate back and forth what's what. You're going to have to understand both tools to know what what would you create in thermal desktop to represent this thing that's in this other tool. But certainly that's been done already, and we see it coming in the future as well.
I don't think I have anything to add to that, Doug.
Okay. All right, well, let's watch for any other questions. So if you have any questions for Matt on OpenTD, oh, here we go. Could OpenTD capabilities be used to co-solve with ANSYS mechanical thermal model or 1D fluid network component with internal hydraulic flows? That's actually, Matt and I both presented this, that we've actually created a connection to ANSYS, and it's to their, here, Matt, do you remember the name of the tool that ANSYS has that ties into their simulation?
Is it SimCenter 3? No, that's not right. No, I don't know. I'm sorry.
Okay. Oh, here we go. System coupling. So ANSYS has a tool called system coupling that that communicates to their tools, and then OpenTD communicates to system coupler. So that's how we've set this up. So yes, there is a way to use OpenTD to co-solve between the two. As presented yesterday, something we're working on that probably won't be in this next release would actually be 1D to 3D fluid flow. So we're working on that next, but right now it's the conjugate heat transfer, including radiation, 1D flows on our side, and ANSYS on the other side. Yeah, somebody repeated a question here. This was already answered about interfacing between OpenTD with mapper objects. So that's already been answered. All right. Not seeing any other questions come in.
Yeah, why don't
Okay.
I pass it back to you, Doug, for
Actually, no, here we have another one. Could OpenTD be used to help automate model checking in the GUI? For example, stepping through color by properties commands.
So not currently. I do plan eventually to add the capability to call some of the model checking commands in OpenTD, but that's not planned for 6.2. The thing to understand about this is that Thermal Desktop is a massive product. It's been around for a long time. There are a lot of features. And to try to implement support in an API for all of them at once is simply impossible. And so what I've been doing over the past few years is finding the highest priority items, create and query a node, and implementing them in order of highest priority. So if you'd like to move something up on my list, write an email to support@crtech.com and we can discuss it.
Yeah,
Oh yeah, and Hume points out, makes a really good point here. Stuff that I haven't implemented, some of our smart OpenTD users have figured out how to use the OpenTD send command, which allows you to send an AutoCAD command to a thermal desktop session. Some of our smart users have found workarounds for things that I haven't implemented yet. And so you may be able to do the things you want to do even if they're not explicitly implemented yet in OpenTD by using the send command, which takes a string that goes to the AutoCAD console.
so I'm going to shift over into, assuming that we've reached into the OpenTD questions, I'm going to shift over to demonstration mode with a few different features. But if you do have any questions that haven't been answered here, you can certainly email support@crtech.com. That is central to all of us, and so that's probably one of the best ways to get the answer the quickest, the correct answer the quickest. But you can certainly email me at doug@crtech.com if you prefer that. But certainly we all have access to the support@crtech.com. I'm going to switch over back to my session. So I understand we should have about 20 minutes left. Just want to cover a few things that come up regularly on questions. Okay, there was another question that says, can we couple with NEO4J? I have no idea what that is, but essentially, the OpenTD is a programming language based in .NET. So really, that's what gives you your limitations. We can speak to what you can communicate with in our side, but we don't know what limitations are on the other side. So I'll have to kind of leave that as that. So common questions that come up, I want to address this a little bit with transmission and refraction. With transmission of radiation through objects, for any number of transmitting faces where subscript T is going to be the total for the entire object, the transmissivity of each surface is the nth root of the total transmissivity. The emissivity for a reflective surface, and you would assign this to either the first or if it's a second surface, I'll call it the last surface in the path, would be 1 minus the current surface's transmissivity minus the reflectivity total. And that makes things a lot easier for everything else, where you simply use an emissivity of 1 minus transmissivity. So if you ignore reflections, you've got two simple things. You have the transmissivity of the surface, which is based on the total transmissivity. And then you have the emissivity, which is simply 1 minus the local transmissivity. for that. Now, Thermal Desktop performs radiation calculations at surfaces. So if you have a finite difference solid, surface coated solid meshes, things like that, N is going to be 2. So you've got one surface as you enter and one surface as you exit. So that's pretty much all you have to set up. Now, if we take a look at, I'm going to switch over to another tool here, and hopefully I can make this transition fairly easily. So here I have an object. I've got a source that's emitting radiation. It's going to go through a lens, and then it's going to be absorbed at a target. So if I look at my optical properties, and first I'm going to look at my symbols because I've set this up to make it easy for me to work with. So I have a lens total emissivity, a lens total transmissivity. Now actually I don't use the total emissivity anywhere, but just for completeness, I have it here. Then the transmissivity I've got set up as the square root of the total. And for the emissivity, it's 1 minus the face transmissivity. So that calculates that out. And if you go through the calculations, it works out so that after you've gone through the first surface and the last surface, you'll have transmitted 90% of the energy and you'll have absorbed 10% of the energy. So in my optical properties, I've actually set this up for refraction as well, where I need to differentiate between inside and outside, but the emissivities and absorptivities are set up here, or transmissivities, and then I have specularity and transmissive specularity. So this is a optical lens, transmissive specularity is 1, and then we'll get to the refractive indices ratio in a second. But then I've just set this up. So each surface that the ray passes through has to have a subset of the total transmissivity and emissivity. So if I look at this first dome, I've assigned the properties outside and inside. So for this dome, it's a sphere, which outside or top is facing the convex side, and bottom in is the concave side. Now going back to my presentation. Oh, let's see. There we go. We'll move on to refraction. For here, I have a refraction index for air is 1. Refraction index of glass is going to be 1.5. So I have to look at the refractive indices ratio. That's the value we have in our optical properties, is the ratio in the direction of the ray. So going from air to glass, it's in air divided by in glass, which would be 1 over 1.5. And I'm going to assign that to the outside properties of my object. So whether it's an outside for thin shells is going to be the direction of where your solids are. But looking at a solid brick, you can assign outside and inside properties. So when you're going from glass to air, you need to have the refractive index of glass divided by the refractive index of air, which is going to be 1.5. And you'll assign that to your inside properties. Now, the values on opposite faces must be reciprocal. So that's a requirement. So make sure you use expressions, because 1 over 1.5 does not equal 0.667. So no matter where you go with that, you'd have to figure out where we start rounding in our significant digits, and you don't want to go through that. So simply put in an expression. It's very simple. Double click the field, open it up, and then there's your expression editor where you can simply type in 1 over 1.5. I'm curious here if I've actually still have this shared. Nope. Oh, I should. So hopefully you're seeing my model again.
Yeah, we can see it.
Okay, excellent. So if I go in my optical properties, well, my symbols again, I have in glass and in other. And right now we'll stick with air. So I'll say 1, say okay, and then set done. And you'll see here, this is what we call smart annotations or TD text. And it's actually tied into my symbol values. So it gives me an update. And so I can go into my optical properties again, and I show glass inside. And so here, refractive index ratio is 1.5 because I've set it up as in glass divided by in other. And then my glass outside is set up here in other over in glass. And then I have to make sure I assign those properties to the correct face. So if I go to my checks, my model checks, I'm going to display top side and display. So anything that's green is the top side. I'm not modeling the solids inside of this. So these are just surfaces. But I see that the top of this disc, that's the bottom of my lens, is actually facing outward. So I have to assign the glass outside to the top and glass inside to the bottom. Spheres are easier because outside is away from the center of the sphere, inside is towards the center of the sphere. So I've set that up as well. Top out is glass outside and glass inside. So if I run this calculation, calculate rad Ks with ray tracing, and I've set it up to just shoot from my source and then figure out how much is reaching the other side. But you can see that the color changes. Red would be at full level, and green or orange means it's been reduced because we should be at 90% of our original radiation. And if we then look over here, and I'm going to post-process this so we can see it better. And let me clear my radiation. Whoops. Here, let's try this again. Clear the radiation display. And so you can see it actually reverses the image on the other side. So hopefully that helps with transmission and refraction. You can certainly model the internal structure of the solids inside and have heat transfer going through and the absorption. So that's all available. Right, this isn't going to be as much of a demonstration as simply discussing how you would do this, but setting up a timed event. I've had a number of people ask about this. You should use output calls to enforce a time schedule. So automatic time steps are adjusted to meet the output calls. And so time steps can be shorter than an output interval if it's required. But the time steps will never overstep an output interval. So you're guaranteed a calculation at that interval. So to set this up, you might identify a submodel for the event, and I'll just call mine submodel. use output calls in the submodel to update the event. So this could be assigning a temperature that's being read as a sensing object for a heater, or just simply a calculation or something like that. And then you're going to set the output interval for that specific submodel to the inverse of the frequency. So if I have a 5 hertz sampling rate, I'll use 1/5, which is 0.2, to give me my output interval. You're going to do this in post-build logic because setting the output interval on the KSet tab sets the output for all submodels. And you probably want to focus this just on the event itself. So the other part of this is you have to assign, on the output tab of the case set, make sure your output submodel is not set to auto, which actually puts it in the global submodel, or to the submodel itself for this timed event. So, and the reason for that is every output interval you reach, regardless of which submodel it is, you will run any logic in that submodel's output calls, and you will also run all the global output calls. And if you choose auto, then all of the outputs for post-processing and text files will be called every event. So you usually don't want that. So try to make sure you put it into a different submodel for that. And so here I have, my example would be a 5 hertz heater that is sampling at 5 hertz. So set a boundary node as the sensing object. So it might be heater.999. And you control when the value is updated. So you can assign a temperature to a boundary node anytime you want. But we're going to do it in output calls heater and update heater T999, which is the temperature of that node, and maybe point to a temperature measure, that's another tool you have that interpolates temperatures on a location. That might be your sensing point. But until you put that temperature into this T999, it doesn't get updated, and the heater just believes that you're running at a steady temperature. Then in the post-build logic, you'll set heater.output, so heater is the submodel name, to 1/5. And then on the case set output tab, you'll make sure that the output is not auto and it's not heater. It could be anything else. It could be main if you have objects in submodel main and you're building it. So that's pretty much how you would set up the timed event. And then the last, now this doesn't get to the edges for setting up contactors, but it does address active display, the display of active faces and face contactors. So when you have a contactor, you're even building a contactor. If you've got an object, say a thermal desktop brick, which I have down here at the bottom of this, you don't know which face is the Z-min or the Z-max or the X-min or X-max and so on. Hopefully you do because maybe you built it, but maybe you don't because you received this model from somebody else. So you're going to put a contactor on here. You create a contactor, select it as the from, select what you're going to do for the what you're connecting to, and then in the from list, right click and choose display faces graphically. And so this will show the object colored by which face is active. So green is the active side, blue, light blue is not active, yellow means both sides are participating, red, wireframe means it's not part of the contactor, or it's not part of the from list. So when I do this, I can shift my window to the side, take a look at how it came out, and make adjustments as I need to get the right face. So I think with that, we're pretty close to the end of our allotted time. And I'd like to thank everybody for their participation and their questions, and a special thank you to the TFAWS staff for putting this all together and um, you know, making do with the situation we're living in now. And I think this has been so far it's worked out really well. Um, Although I will personally say that I hope I see everybody next year at a in-person TFAWS.